Right. Now, in this module we are going to learn the basics of Sapphire laser, what is there inside and how to use it. But before that, this is what we have learned and this is where we ended the last module. We talked about curl length mode locking. Curl length mode locking means because of the Gaussian distribution of a TEM00 mode, you have greater intensity at the center of the beam and it falls off as it goes towards the edge. This brings in an intensity dependent refractive index, which sort of acts like a lens. It is called a curl lens. And since pulse light, so it focuses the intense beams and does not focus beams that are less intense. And since pulse light is intrinsically more intense, what this curl lensing does is that it can select pulse light over CW light. You can do it actively by putting in an aperture in the path of the beam, but that is not even required. The optics usually take care of it. This is what we said and this is how pulses are produced. So, femtosecond pulses are produced by curl length mode locking without us having to do much. In subsequent modules, we are going to talk about active mode locking, where we have to introduce something and get the mode locking done. That is, we have to use something called acousto-optic device, but here that is not even required. Thermal lensing takes care of it. And of course, why is it that we get femtosecond pulses and not picosecond pulses by thermal lensing? Because in femtosecond pulses intensity is much more, right. You are mode locking many more pulses, many more modes are locked. That is why pulse width is so small. So, this is what you can get by curl length mode locking. If you want picosecond pulses and nanosecond pulses, you have to do something. Okay. We said that this is the advantage of curl length mode locking, it produces pulses. Disadvantage of curl length mode locking is that it also brings in chirp, which effectively is going to broaden the pulse. So, before we can think of making a laser, we have to correct for this chirp. And how do you correct for this chirp? The answer is very simple. Once again, you can go back to this analogy of competition, right. So, I enter a running race with Tanuja. All of you agreed that Tanuja is going to win hands down because she is a faster runner, but I do not want that. I want to reach the end point at the same time as Tanuja, even though I am a slower runner. So, if I am powerful enough, what will I do? I will make her run more and I will run less. I will take a shortcut, I will not let her take a shortcut, right. So, difference in speed has to be compensated for by altering path length. Okay. It is that simple and that is what is done to compensate for chirping. What you have to do is whichever path, whichever light is leading has to go through a longer path. The frequencies that are trailing have to go through a shorter path. Okay. And this is done quite easily by using prism pairs. In fact, it is enough to use one prism pair. I am going to show you an arrangement using two prisms, but what is more common and what we have inside the laser we use is two pairs of prism. And the job of this prism is to do compensation for what is called group velocity dispersion. What is the meaning of group velocity dispersion? The separation in time of different frequencies due to different velocities in a medium with a finite refractive index, that is called group velocity dispersion. We are trying to compensate for it. Okay. So, what do? Say you have a chirp pulse that has gone in. You can see the chirp, right. Here the wavelengths are more, here the wavelengths are shorter, greater frequency on this side, lesser frequency on this side. Okay. So, you make it go through a prism. Okay. Everybody knows what happens when it goes through a prism, it gets dispersed. Okay. Then introduce in the path of the light another prism which is facing opposite and the angles have to be same. Then what will happen is, look at this path. What is this color on this side on the top? Yeah, green, red. What is the color at the bottom? Yellow. So, what we are showing here is that red has travelled less and yellow has travelled more. Then you put this, then it will become a collimated beam, and I will show you in a moment why what the advantage of using two prism pairs is. Okay. And then it goes to another prism pair, then again they are brought together and it goes out as a beam. So, here the inherent assumption is that the light marked in red is trailing and the light marked in yellow is leading. So, we have given a bigger path length to the yellow beam, yellow I am not saying yellow color, the color that I have used to depict the beam here, and I have given a smaller path length to the frequency that I have depicted in red. Okay. So, if red was trailing with respect to yellow in this region, then that would be compensated for. Have you understood? So, this is how GVD dispersion is done. Are we clear? Now, what is the advantage of using two prism pairs instead of one? The advantage is you can have tunability. How do you have tunability? And this is what we have in our tsunami laser. When we open it up the next day, we are going to show it. In tsunami laser or in many other lasers which are tunable, what you do is you introduce a slit in this portion. That is why you require a collimated beam, otherwise it will be very difficult to calibrate. Okay. Suppose you have this slit in this region, then this part of the light is going to go through, other part will be blocked. Okay. So, that will be the modal wavelength. If I move the slit, oh, I made some animation, but I think I have goofed it up, but I think you can understand. If I move the slit the way it is drawn here vertically, I bring it down, then the light that is depicted in yellow will go through to a greater extent. Move it up, light that is depicted in red will go through to a greater extent. This is how we get tunability, and I am going to show the picture of a laser at least today. There we will see how we do it, and when you open it up we will see it even better. Okay. This is the advantage. If you use only one prism pair, then it is difficult to have tunability, then it is whatever the system gives you, the spectral maximum. But advantage of using two prism pairs is, in addition to compensating for GVD, you can have a tunable output. Okay. Right. Now, the laser that we use in our laboratory is a titanium sapphire laser. What is the meaning of a titanium sapphire laser? Sapphire, I think we discussed earlier. What is sapphire? What is sapphire to a chemist and what is sapphire to a layman? To a layman, a sapphire is a precious stone, right? You make a pendant out of it or you wear it on a ring. To a chemist, what is sapphire? Aluminum oxide with some doping, right? So, here the doping is titanium. So, you can read how it is made. It is a titanium oxide, aluminum oxide melted together and so on and so forth with a particular level of doping. Now, aluminum oxide is the matrix. It is the titanium ion that is the actual active ingredient. There can be other depictions of the energy levels, but this is one that is there in tsunami manual, and this is what describes the system fairly well. Ground state is a doublet T2G, excited state is a doublet EG. Okay. And when you excite, I am going to show you the spectra. You excite at say 530 nanometer or so, you can excite there. But then post excitation there is an ultra fast relaxation to the 0th vibrational level, and this is where the emission occurs from. And you can see that the equilibrium bond lengths well the minima of the two potential energy surfaces, not a good idea to talk about bond lengths right now, but minima of the potential energy surfaces are not in the same position, right. So, when the emission takes place from here, this is where you reach. So, this energy gap is more or less 800 nanometer equivalent. That is why you excite using green light and you get what they have called IR light. You see it better in this absorption and emission spectrum, right. So, you can see absorption spectrum is more or less from 400 nanometer to 650 nanometer. The maximum is somewhere near 500, 550, that region. Emission starts at 600 nanometer, maximum is at about 800 nanometer, and it goes all the way up to 1050 nanometer or so. So, this is what you get to play with. You can excite anywhere here and you can get emission anywhere here. Usually, one uses 532 nanometer excitation because that is a very robust laser that is already available, neodymium YELF or neodymium YAG laser. Okay. That technology is so robust that it does not make sense to try to pump with anything else, and in any case it more or less matches the absorption maximum. Okay. So, that is your pump laser. Pumping is CW in this case. You do not, we are going to talk later on about cases where pumping is by a pulse laser, but not in case of a titanium sapphire oscillator. Pumping is by CW green laser. Okay. And this is where the emission takes place. Now, looking at this diagram, the energy level diagram, can you tell me what kind of a system is it? Is it a 2 level, 3 level or 4 level system? 4 level system. What kind of output do we expect from a 4 level system? Continuous wave, right. So, intrinsically you expect titanium sapphire laser to give you CW output, and it does. Mode locking takes place because of your Carl Lenz effect and so on and so forth. Now, with that background, let me show you one of the earliest successful designs of a titanium sapphire laser. This is called the Murnane Kapteyn design. Well, Kapteyn and Murnane are two professors of, I think, University of Colorado at Boulder, but they have for a long time now launched a company which is quite successful, not so much in India, but across the world. It is called KM Labs, and claim to fame of KM Labs was this kit that they used to sell at one point of time, where you have everything that you require to build an oscillator, and you are supposed to put it together and make a sapphire laser yourself. That kit is still available once again on demand. This is a very simple design, but it takes a bigger space. So, this Kapteyn Murnane laser takes up say 2 feet by 2 feet kind of space on the laser table, leaving out the pump laser. So, a squarish kind of design. So, this is how it works. Pump laser comes in, and then so you see one thing that we will say without going into much detail here is that for solid state lasers, pumping has to be coaxial. For dye lasers, it is okay if the axis of lasing is this and you pump like this. Not so for solid state lasers. So, pumping has to be more or less along the same line, same axis along which lasing takes place. So, that is achieved always, and I am going to show you the ray diagram of our own sapphire laser later. That is always used by using one mirror, that is your dichroic, allows green light to go through, does not allow red light to go through. So, this M3 mirror that is shown here, it is a dichroic mirror. Green light goes straight through, in fact, even M2, and red light is reflected. Okay. So, this is your pump from 530 nanometer, typically 4 watt, 5 watt, 3 watt, whatever it is, CW. It is focused on the laser rod, the titanium sapphire rod, which is shown here as a red trapezium. Okay. And then emission from this laser rod is captured by these two mirrors. These are concave mirrors, I hope you can see, and then they are focused back onto the rod. So, see, we talked about Carl Lenz mode locking. So, this is what sustains mode locked operation even without using a using your an aperture, because the mirrors are aligned in such a way that they are exactly focused where this pulse beam is supposed to get focused. So, anything that is not focusing will not be in the axis of lasing. That is how CW is gotten rid of. Sometimes there is a little bit of CW contamination, you have to play around with the optics and get rid of it. Okay. So, now let us go one by one. Let us take M2 to start with. Okay. M2 catches this, focuses it here, and then it goes this side, goes through a prism pair. You see here in this design there is only one prism pair. What does it mean? You do not have tunability. Then it goes and hits M4, which is a plane mirror, and it hits M4 exactly at right angle. So, then it is sent back. It retraces its path, gets focused here. From M2 it goes to M1. Again M1 is a plane mirror, and then it goes to an output coupler, which is a partially reflecting mirror through which you get the laser out. Okay. Quite a simple design, not very difficult to make, provided you have all the distances right. And then the reason why Captain Martin kit became such a hit is that everything was specified. So, it was like Lego, you have to put things together in the right place and you have your laser. And to always titanium sapphire laser starts operation in CW mode, because it is 4-level laser, right. So, you have to bring in some kind of disturbance in the cavity, and that is what kick starts pulsed operation. So, the way in which, I should say that this figure is from PhD thesis of D.S. English, who is a professor in somewhere in the US right now, I forgot exactly where, and I have used this laser as a postdoc. So, what we would do is we would tap a mirror. It is an open laser, unlike what we now use. So, you go and tap a mirror like this, or just disturb the mirror a little bit, and then mode locking is done. Okay. What we have in our lab looks significantly more complicated. In fact, if you look at the manual, it looks even more complicated because other components are included there. That is what took a lot of time today. I had to erase all those things that we do not have. Let us see if we can understand the optical layout of the spectrophysics tsunami laser that we use in our lab. Other lasers from Coherent and other places have more or less similar layout, but every company has its own design. So, here we will spend a little time on this because we want to understand exactly why what each component does. So, you have the pump beam coming in from here, from the left. Okay. There is a Brewster window. When we talk about nonlinear optics, we will discuss Brewster effect. It goes in. So, this is the entry point of your tsunami laser. Okay. Go straight. P1 means P for pump. P1 is a green reflecting mirror. So, P1, as you see, is a plane mirror. Goes to P2, which is a focusing mirror, because your pump beam also has to be focused at the crystal for optimal operation. P2, a curved mirror, concave mirror. Then see, it is going through M3 for the same reason that I discussed when we talked about Captain Martin design. M3 again is a dichroic mirror, allows green to go through, reflects red, and it is more or less coaxial. So, it goes, hits disapphire rod, and then it goes straight. I am talking to the pump beam now. Pump beam goes through M2, which is again a dichroic mirror, and then there is a beam dump. That is where it hits, and then it has no further role. From this disapphire rod, emission takes place. Once again, similar to Captain Martin design, you have two mirrors, M2 and M3, and here you have the high reflector M1, plane mirror. The job of plane mirror is to just send it back, send the beam back and make it retrace its path. Then from there it goes through M3, M4, which is a plane mirror, M5, which is a plane mirror, and then it goes through what we have discussed already, 2 pairs of prisms. What is the job of 2 pairs of prism? GVD compensation, and this here is the tuning slit in the portion where the beam is collinear. Okay. So, basically when you change color using a micrometer screw gauge, you move this slit up and down. This is actually vertical. Then M8, M9, well, this is the prism pair, this M8, M9 are actually increasing the length between P3 and P4, well, PR3 and PR4. Then there is something called acousto-optic modulator. Hold on, we will come back to it. And then it goes to your output coupler, okay, and then it goes straight. There is something called beam splitter here and fast photodiode here, we will see what they do. But before that, suppose you have a tsunami laser. Here of course, we have not had much problem over the last 12 years that we have had it, but suppose your laser is not lasing, it has happened once or twice. How do you get it to laze? And this is true not only for a Ti-Sapphire laser, any laser whose cavity you have access to. How do you make it laze? Generally, you do not have to do much with the pump beam, but you must ensure that the pump beam is horizontal. In any good alignment, all beams have to be horizontal, unless for some design purpose they have to go like this. Otherwise, horizontality is very, very important. And here you can see why it has to be horizontal. If it is anything but horizontal, the entire path gets messed up. Okay. So, horizontality of pump beam is an issue. Then, okay, now Ti-Sapphire emission is there. It is not lazy, you put in a card there, you will see the fluorescence on the card, provided your eyes are not as bad as mine. You have to be able to see red nicely. Okay. So, you can, there are 2 arms, isn't it? One arm towards M2, one arm towards M3. First thing to do is falls on M2, hits M1 and comes back, right. You have to ensure that M1 is aligned in such a way that the beam retraces its path. How do you do that? You take a white card and punch a hole in it, right. Hold the card in this beam and make sure that the beam goes through while coming from M2 to M1. Now, when it goes back, let us say this is the hole in the card. This is how the beam goes from M2 to M1, hits M1, comes back. Now, if it is not going to, if it is not retracing its path, it will hit here or here. So, you can see it on the card. Then you have to play around with controls of M1, so that it goes through this, right. Then this M1, M2 segment is aligned. You have to do the same thing here, because fluorescence that is captured by M2 has to retrace its path while going back to the crystal. And of course, you understand the moment you touch M2, not only is the Ti-Sapphire rod to M2 alignment changed, M1 M2 alignment will also get changed. So, you might have to do it more than once, several times. Do the same thing on this side, and then see the beam goes this way and comes back. So, once again you have to take your card with a hole somewhere here between M3 and M4, play around with M4 control and make sure that your light going in this direction and this direction travel in the same path. When that is done, you take out the card, you will see lasing. This is something that unfortunately we do not have to do on a daily basis anymore. I am saying unfortunately because once you do it, you become an expert in alignment. If you do not do it, it is a black box, and if you ever have to do it somewhere, it requires a little bit of practice. Of course, now as we are going to show at the end of this module, things have become toys, you cannot do anything. So, maybe that skill is not even required anymore. This is what the laser looks like, and again we are going to go to the lab and see it. We have seen it once already. See, what you have is, this is the side through which the pump beam enters. no sorry, this is the side through which the pump beam enters. From outside you just see some controls. Okay. In our laser we do not even have this birefringent filter wavelength selector. This is a generic diagram. We have these two knobs. What are these two knobs? These are vertical and horizontal controls of the high reflector. Which one is the high reflector? This one, right. So, this blue and green knobs that are there, green is for earth, horizontal, blue is for sky, vertical. So, these are horizontal and vertical controls of the high reflector. That is what one usually plays around with. In the other end, we have similar controls for the output coupler. Generally, we do not touch it, because the moment you touch both, you are sort of shifting the beam completely, and if you are not careful, it can get misaligned. But sometimes we do have to touch output coupler, because condition of the lab can change from time to time. Okay. We do not have this GTI dispersion thingy. We do have these two micrometer controls here. One for prism dispersion compensation, one for wavelength selection. What are these two micrometer controls? One of them changes the distance between the prisms. So, when you change the distance between the prism, you are essentially changing the path difference among the different modes. The other one moves the slit up and down. Okay. So, by moving the slit up and down, you select the wavelength, the modal wavelength, and by playing around with the distance between prisms, that is how you maximize GVD compensation and ensure that you get a good optimal pulse. Okay. Now, there are some problems with this tsunami kind of laser. One problem is that the cavity is not sealed. So, if your lab is not absolutely dust free, dust can get in and spoil your optics, so regular cleaning might be required. Fortunately, that is not the case in our case, and that is not the case for almost all ultrafast labs in India. Nobody would invest so much in a laser and keep it in a dirty room. But there is another problem of the cavity being not sealed. The problem is that no matter how much you try, you cannot have a room that is absolutely dry. Your relative humidity, we use dehumidifiers and all, but at most we can go down to 40%. It is important that we go down to 40%. But then you can try and use industrial dehumidifier and go down to maybe 15%, but that is not good for your health. Nosebleeds have been reported in labs where too much of dry atmosphere was maintained. So, some moisture will be there, okay, even if it is 14%. And water absorbs in the region of 950 nanometer onwards. So, if you are going to tune it, then you do not want moisture in the cavity. So, tunable range is severely affected by the presence of moisture. So, in a tsunami kind of laser, if you want to go up to say 1000 nanometer output, then there is no way other than purging the entire cavity with dry nitrogen. And we have done it a couple of times, and I do not want to do it ever again. The one nitrogen cylinder gets over in one day. You do one day's experiment, the cylinder is always on, right, and it is an open cavity, nitrogen is going out. So, it is first of all it is cumbersome, and secondly it is very highly nitrogen intensive. I do not want to do it. So, because of these problems, and also the other issue is technology is moving in a direction where everything has to become a black box. User should not worry about how things are. Of course, the purpose of our course is exactly opposite, but that is how things work. You are a biologist working on 2-photon microscopy. You do not really want to know about modes of lasers and how they are coupled and so on and so forth. So, this is the state of the art, and we have shown this already when we went to the TCSPC lab earlier. So, everything is sealed in a container. Advantage of this is that you can have full range of tunability. 690 nanometer to 1050 nanometer at the click of a mouse. Disadvantage is anything goes wrong inside this, the laser has to go back to the factory because it is hermetically sealed. It cannot be opened anywhere other than the factory where humidity, temperature, everything, air quality, everything is maintained very rigorously. Okay. The question that should come to one's mind, and this is actually a laser in which you have the pump laser on one side and you have the Sapphire laser on the other side. Now, we should have a question when we see this. This here is the laser driver. Why? We had said earlier that you need some kind of a cavity length to have pulsed operation, okay, round trip time and so on and so forth. So, in such a small thing, how is cavity length maintained? And that is the diagram I was looking for and unfortunately did not find this morning. If I find it, I will include it in the presentation and upload. So, what you have there is that you have this Sapphire crystal and you have two large mirrors, and the alignment is such that the light bounces off these mirrors many times. So, even though the separation between the two mirrors is not much, the effective path length is the same as what it is in tsunami. That is how compact sealed lasers like MiTi work. Okay. So, what we have done today is we have started with principle of mode locking, curl length mode locking, and we have given you a little bit of idea about construction of lasers. We have not talked about certain things yet. One is, if you remember that diagram, we have not told you what the fast photodiode does. We have not told you what the meaning of AOM is. So, in the next module, we are going to go to the lab, open up Tsunami and show you. After that, we are going to talk about what acousto-optic modulators are, how they can produce pulse picker, how they can produce pulsed operation. I told you already that you do not really need acousto-optic modulator in this cavity. Why is it still there? It is still there because there is this technology called regenerative mode locking, and we will discuss that after we have talked about acousto-optic modulators. And we will also talk about electro-optic modulators like Pockels cell, which can give you not short pulses, but large pulses, but in this context which are useful in switching the laser pulse outside the cavity. Once we are done with this discussion, we will talk about how amplification of laser is done, and then we will talk about optical parametric amplification. Okay. So much for today.